All right, how does that work? Finally, cool. Hello everyone, thanks for showing up in person. It's crazy that we had to wait almost 3 years to get you back here, so appreciate a lot that you all came in. I feel like a deer in headlights here, so I probably can't see you guys in the first 3 rows, and I won't see you guys because of my glasses in the last couple of rows. So bear with me, I somehow see some blur, and anyway, but you're a real human being, so that's fantastic. So for the next 45 minutes, we're going to talk about multi-tier fabrics. And my name is Lucas Kretter. I'm going to guide you through this whole story, and I hope we're going to make it in time. We try to bring new things in to make you guys think and to look at not just the deep technical details, but also talk about architecture and design. So we bring here a little bit more on the design side and make you think about leaf-spine networks and what you could do next. If you want to continue the conversation with us beyond just this room, there is something kind of a WebEx room. You guys can join, ask questions, and I'm sure that I find somebody who answers all of them. While presenting, I won't do it. For the abstract, we talk about something of a gentleman called Klaus way back in the 70s or 60s even, or even 50s. And these Klaus networks have different names today. I mean, a gentleman named it. His name is on it, but fat tree, leaf spine, if you want, so are some of them which we are going to talk about. So I will jump a little bit about introduction. I will go and give you some names and nomenclature, some design and sizing considerations, and that's actually one of the main parts in how you size such a leaf spine network, that it fits your specific needs. So I give you guidance rather than just you must do it in this very specific way. I also go and highlight some of the 3-stage versus 5-stage design and what you actually could look at to identify what works better for you. And also in these networks, in these designs, what are the platforms to choose for? I mean, these days we can build modular switches, we can build fixed switches, and what are the attributes which these type of switches bring to you and how they fit into this design section, and then a little bit around the data center or or how we bring it in your data center up there. If you don't have enough of me or some of my colleagues, I have a whole bunch of companion sessions related to this or others. So we're here, Monday afternoon, first session on the bottom left in yellow, and then you have a whole bunch of other sessions you can follow if you're interested in. We have something called learning maps. You can also figure them out on the session catalog, but if you feel that's more what you want to hear what you hear today from what I'm doing, you can go through this, and some of them are presented by me, some of them by my colleagues, but we have a good split and speaker these days around. So we went through the introduction already a little bit. I'm going to jump right into the middle, given we have 45 minutes or 41 in the meantime. So paradigm fundamentals is our first step where we go design evolution, and then a little bit of conclusion, some points you probably want to look at when you're going into your designs, and some things to recap when you go and build such designs. So let's go. You guys ready? I know I'm speaking too fast, but try to pace it out, keep calm. So, leaf spine. That's a leaf spine topology, by the way. So you have on the bottom the L's, the leaves. We have on the top the spines. So the spine is kind of my backbone of this story, like we all have a spine in our bodies, or you have a spine in a tree. And the leaves are your fingers, which spread out, the fan out, and a tree has leaves as well, right? So as you spread out the things. Now, as said previously, there are variation of names of this, and it's actually all the same thing. So you see the first one here, a fat tree, a folded clause, 3-stage clause, or a 2-tier network. So where are these different things coming from? Why are there different names? It's just in the conversation you might want to look at different pieces. And for example, when we look at the 3 stages, you're talking about your 3 stages of latency you will have in the network. Leaf is latency, Spine has latency. The other leaf has a latency. So every traffic will go from a leaf to a leaf in all of these cases, so 3 stages. It's one of the terms. Why 2 tiers? Tier number 1, leaf. Tier number 2, spine. So depending on what you're actually talking about, you're meaning the same thing, but make sure that you don't say, I build a 2-stage clause with 3 tiers of network layers. That cannot work. Right? Okay. So there's a little bit about nomenclature in there and a bit about the paradigm around these leaf-spine networks, and I probably haven't said anything new to you guys. But all over, the idea behind these networks, or these type of networks, is scale out. You don't want to scale up. And I'm going to explain you a couple of pieces around scale up and where you actually ended up in the end of scaling up. And what it means that when you go from the highest possibility of your current design to the next evolution of it, meaning I need to add more leaves or I need to add more front panel ports. These are all attributes which come in these scale-out networks, where more leaf gives you more ports, more spines gives you more bandwidth. Very deterministic, right? Horizontally scale out, not scale up. Another attribute which you get out of these networks, click probably one too far. Here we go. Is the N+1 redundancy. I was here when we built always these 2 big boxes, and when one failed, 50% outage, right? And probably when it failed in the early days, either you had to go and configure the IP address from your left box to the right box, or you had something like first-hop redundancy protocols. And when the first-hop redundancy protocols were there, it always took a lot of time to converge. And guess what? There are 2 or 3 things you probably never looked at in these scale-up networks or in these active-active networks or 2-box networks, 1+1 redundancy networks, which is how long does it take to have all my MAC tables, my ARP tables, which you want to have for all your host connectivity, being converged. I tell you for sure, I saw ARP convergence early days for a long, long time, because not everyone learns in the same pace and the same way. So keep that in mind on the older network designs, but also here that we don't have this issue anymore when we go to newer designs. Mainly 2 reasons. 1, you don't have a centralized gateway on the spine. So it's not 4 learning things, it's all the leaves learning things, right? With this, much smaller tables, much smaller MAC and ARP tables, and you get in there. The spine is just a backbone for us. And then the impact of a spine failure with 4 or with 8 spines, or even go further to 64, 128, 256 spines, the percentage of impact to the overall network goes down because we distribute data, traffic all across all the possible ways, across all the different spines. Then we have something else. In the past, in our very hierarchical access aggregation 2-layer networks, we had very, let's call them old applications. Probably everything was running on the single server what was necessary for that application to work. These days, and over the last 5, 10 years or so, we started to build more distributed application. So potentially when you access from your PC the front end of one application, which we call one connection, the result of it in the data center, because of the nature of the distributed application, might be up to 7 or 8. So you need bandwidth for that. Let me make an example. I go to a web server has to connect to the database server, or to the application server, for example. Now that's one part. Maybe your web server's image runs as a VM, and the VM runs on your storage. And the storage is an IP storage, so you already have 3 to 4 connections you're doing horizontally in your data center at that point. So keep in mind this north-south traffic versus east-west traffic. These designs are optimized for east-west, optimized for modern application, optimized for distributing load across all of them. Then other pieces which are coming in is oversubscription. I cannot give you the one right math for it. It's what you need for your applications mainly. If you have certain type of applications, like IP storage, we even talk about undersubscription these days. And the under subscription, which is 0.7 to 1, for example, is to accommodate very high buffer or very high traffic spikes, which you don't want to use the buffer. You want to actually let it go through. And that's where oversubscription, undersubscription, bandwidth requirements comes in. You literally need to know a little bit about your application, otherwise you have to go in the most safest way. And the most safest way could be very expensive. So we have to expand to the needs of the application, to the needs what we actually connect there. Now, with this, there's always this question, so how many spines do I need then? Please, can you tell me? I can't. It depends. It literally depends on what you want to do. But I give you a couple of examples, and it comes back to what do I actually attach to my network? So I don't know if we have a laser here. Let's see. No, we don't. So I decide I have one rack, or per rack, I have 48 servers. That's 48 ports, right? I want to have redundancy. That means I need at least 2 switches within the rack. So this is a requirement I could have. So we know we have 48 port requirement by 2 for the redundancy. And potentially, it gives me the requirement of at what speed these servers are attached. 1 gig, 10 gig, 25, 50, 100, 200 these days. So it becomes a known design attribute for you in how you can design your rack. And from there on, you could actually define on what is my next layer required to accommodate. So let's say we don't want any oversubscription. We have 48 ports, 25 gig, gives me somewhere 1.2 terabits, which I need to accommodate if there is no oversubscription needed. You guys agree? Oh yeah, I did the math right here. No, I've probably math errors in there, but we can keep it there. So if I want to go 1-to-1, we need 12 100 gig ports out of this leaf switch, right? That gives me a 1-to-1 oversubscription, right? 2.5 times 48 is 1.2, 1.2 divided by 100, 12, right? Super simple. So when I select my leaf switch, I need to do 2 things. I need to accommodate the attribute of the downlinks, the speed, the oversubscription, and the uplinks. So I can go and figure out I need 12 spines. And I make it simple here, that we don't have to go in crazy math and say I do 3 spines and use 400 gig ports. Possible as well, but let's do the easy math, which goes along here. So when I need to build this with 12 spines, what does it mean overall? Overall for my fabric, I need to do what I can do with these 12 spines. So we have an 8-slot modular chassis. Let's take that 8-slot chassis modular. We're saying we have 3600 gig ports per line card, right? That gives me somewhere in the 288 spine ports. That's the maximum I can accommodate on leaf, right? I cannot go and have more leaf than I actually have ports in a spine when I decide that every leaf has to be symmetrically connected to the spines, right? So that's kind of the end there. As a result of all of this, we're getting 288 leaves. We are getting them multiplied by 48 ports, which gives me somewhere north of 12,000 ports, which my fabric can scale. At a one-on-one oversubscription, as you can see there, okay, sorry, it's 13,000 ports, 30,008, sorry for that. Now, in the oversubscription and with the 1 terabits uplinks, etc., you get the overall fabric bandwidth. And this is just the total accumulated bandwidth you have available between leaf and spine. So that's somewhere at 350 terabit or something like that, if we want to build it this way. So I'm here at the maximum scale of my spine as it's currently built. So I hit the limit, right? I'm done. Nothing more. Because I have 288 ports, I cannot put something on top of it when I have 288 leaves. I don't have any ports left. So what can I do when I want to go further, when I want to go beyond these 13,000 ports? And that's using a 16-slot chassis. 16-slot chassis, we're going to have 36 ports there. So I'm just continuing the whole story. So from 288 leaves, we go to 576 leaves. And obviously, the bandwidth gets higher as a part of it, and so on and so forth. So I can go and at least double my leaf count and respectively my port count for access ports, right? 28,000-ish something. Now what else can I do? I can go from there and increase the speed from the 8 slot over to, instead of 100 gig line cards, can go to 400 gig line cards. I think that's the math example which I'm going to do here. You see, I stick at 8 slots, but I have 400 gig ports, 36 of them. I break them out, or I keep them at the respective bandwidth, depending on. But when I break them out, I get somewhere like 1,000 something leaf, multiplied by the 48 ports, etc., gives you your host front-ending there. And now we're moving from 13,000 ports, which we had with the 100 gig, we're moving to somewhere, what is it? 55,000 ports with the 400 gig. So same chassis, right? If it can accommodate the slots. So I can play these games, but have you seen what I did? From 8 slot to 16 slot. What does it mean for you as a network operator? It's disruptive, right? Do you have space for 16 slots? Maybe you calculated it in the beginning, but even if you have space, you have to remove that thing out of the rack, take another one, put it back in. Or when you change the line cards, you might have more components which also needs to be changed. Or maybe you have to, well, not maybe, but you have to use some cabling attributes, right? At least unplug and plug in. So in a leaf spine network or in a 2-tier network, your scale is really very linear. Depending on the ports you have available in the spine, you can do the leaf part. Is this really true scale out? It's scale out till you hit the wall of the scale up of your spine platform. So in the sense of design, it's a scale-up network. In the sense of how the topology looks, it gives you the attribute of being a scale-out network. But you decided to use all 288 ports, or 576 ports, or 1,150, 2 ports. You decided that we hit the wall at that point. So you're the network designer, you're the architect, you want to do more. You want to look forward to. And what are attributes to scale? Again, they're very, very specific and ending you up in a scale up instead of a scale out network. And by the way, the oversubscription ratio doesn't play a lot into that part. You can maybe go from a 100 gig port and do 4 times 25 if it's enough for you, right? That's how you can increase the oversubscription quite dramatically when you think from 100 gig down to 25 gig for your uplinks, but that's another one which you can do that. Now, how do we scale 2-tier networks? How could we scale them? What possibilities do we have to scale them? I put a whole bunch of ideas there, and that's all what I went through in my earlier life when we started building a network, we started building a data center. Then we added new line card, we added new chassis. Oh, by the way, new chassis again, new line card again. So it's kind of a, what do we call it? The circle of life, if you want, so, or the insanity on the other side. So let's try to, when we do this, apart from scale, because maybe you guys don't have that scale requirement, what else should we think about? And that becomes now much more interesting. So what is my failure domain? Change domain. How many different teams do I have to ask in a single data center network, in a single fabric, if you want so, if I have 1,100 leaves? How many people do I have to go ask and beg, can I please get a maintenance window for the change? Or if something goes south, how many other parts are affected of it? I have the beautiful job of standing up here and just telling you about it because nobody will call me at 2 a.m. in the morning, but in my past life it actually happened. It happened. Then beyond just the leaf and the port scale, what's your actual overall scale you can accommodate? I mean, you have routing protocols, you have routes, you have MAC addresses, you have a fabric solutions. I mean, we have, for example, VXLAN EVPN. What is the maximum VTAP scale we do? 256. So what does it matter that you have 1,156 ports or 52 ports coming from a spine when you can only do 256 leaves? Additional things which are beyond just the number of the ports up and down. And then SLAs, downtime, all comes in. And then I want to show you one more thing you probably never really thought about when you built a leaf spine network, and when you built a leaf spine network with a modular switch as a spine. So you actually built 2 tiers, right? Leaf, spine. Well, you actually built 5 stages. Leaf, line card, fabric module, line card, leaf. 5, right? It's okay, guys, it's okay. But instead of what you actually think you built, you really built the one on the other side. You just don't see that in your hands. But a modular chassis is a little leaf spine network, if you want so. It's a leaf spine network which you don't see, which you don't touch, right? So here are the stages again represented. You see the stage 1 on your leaf, stage 2, stage 3, 4, and 5. So now, as we know this, what could we actually do to really get 5 stages? And how we can leverage all these 5 stages for our scale-out architecture. This is just some additional info. But before we go there, remember one thing. Every stage has latency. I normalized the latency just to make it a little bit easier in math. It's actually not that bad as you see here. A fixed form factor switch is generally somewhere around 1 mic of latency. Okay, it's a single chip switch. Now you go to a modular one, which has line card, fabric module, 3 switches, 3 chips, right? At least 3 chips. So I would guess I get 3 times the latency, right? It's actually true. It's not 3 times, it's maybe 2.2 or a little bit less, but you're increasing actually your network latency, and you limit your scalability in these cases. And then on top of that, I don't know where I have that, you're losing cut through. In the industry, 99% of all modular chassis, 99.999% of all modular chassis operating in store forward. Which means your latency is not only higher, but it's also variable depending on packet size, because you have to first learn all the packets, store it, and then you forward. So keep some thoughts about all of these things. And you also have a couple of other points which I'm just running over, but in the modular case, do you really have the possibility to influence the line card to fabric module communication? You don't, right? So troubleshooting becomes something out of your hands very oftenly. Now, I'm telling you guys this because these are a lot of thoughts when we talk to the very large cloud providers, let's call them this way, which they bring to us and say, hey, these are my problems, please solve them. And I think it's good that you guys learn from how they think, or maybe you already figured that out before even showing up here, but that's the story, right? New angles to network design problems, and these are some of the basic, or sorry, not basic, some of the background things you probably, or maybe you have not thought about. So with all this knowledge, why do we still build 2-tier networks and put these big fat spines in? I don't know. I mean, it's an habit. I still do it. Put a bomb together, easy, like a couple of boxes. I don't have to manage all of these boxes because the line card and the fabric module does it at once. But today in the world of controllers, I think some of this thing goes away. If a controller can hide the functionality of 3 additional network layers, we're not going to 3 additional ones, bear with me. But if the controller can hide a layer of 3 additional network layers, but I get a better outcome out of it, that's something I would like to look at. So maybe you want to look at this as well. So we go a little bit into design evolution. And in the design evolution, you guys know the status quo. We just talked about that. And then we can do something which is a little bit beyond the status quo. We add an additional layer on top there. But adding that additional layer on top, it's nothing really new, right? We already did that. And the crux in this is, very often, I say all of my spines connect to all of my super spines. Now, how many ports more do you need in order to accommodate all these different layer interconnects, which has a cost factor, performance factor, management factor, and so on and so forth. So we can actually do something a little bit, should we say fancier, and look at the layers in a different way. Let's look at the layers more. I'm talking about the tiers, the layers, the stages. Let's look at them a little bit more as, instead of a switch, let's look at it what the chip provides me, what we call an ASIC these days, and the chip with all these ports, and how do I going to connect these different things in an interesting way. So let's move forward to this piece where we do a 5-stage network with a leaf tier, with a fabric tier, and with a spine tier. You can also call it leaf spine, super spine if you want. There's so many different names. I'll just call it here leaf, fabric, spine. And when we want to build this, these are the 4 attributes which we want to go after. Simplicity is key. Everything should be easy from a design principle. So every piece you do should be repetitive, and you see that also as we go into the redundant and repeatable, because you do everything always the same way, and you connect it and you use it always the same. So simplicity is key. Scale as you go. I want to start with 12 leaves, and I want to go to 24. I want to go to 128. I want to go to 256, 256, all the way to 1024. But I don't want to buy all the gear at once, and I want to do these building blocks going forward, so I want to scale as I go. And when I fail, when something goes wrong, first of all, I want to see it, and it should fail fast, right? When it fails, fast, deterministic, no brownouts. So these are these classic principles of network designs. And I guess you guys are all looking at these pieces. I'll just give you a different perspective of this. This is how the Cloud Titans build, if you want so. We do scale out in a multi-tier infrastructure. And when we want to build these scale out in these multi-tier infrastructure, we have to do one step back when we start doing our designs, and that is, we're not designing for the maximum amount of leaves connected to a spine. What does it mean if I do the math for my maximum scale of leaf per spine? It means I cannot go to any next step because my spine is full. Full means door closed, scale up, we're going away. So we need to go for a different way, and you see here my Fabric 1 has only 128 leaves. Remember when we did the modular stuff before? So I have plenty of ports left in the spine. I actually have the same amount of ports left downstream between spine and leaf, as well as from my spine to the next level above, which allows me to do a one-to-one oversubscription from any leaf in the network to any leaf in another pod or in another data center or in a hole. So in these designs, it doesn't matter really how many ports you have. I just give you one example, 128. We can use a 64-port, 400 gig spine box, 2 rack units. You break them out in 100 gig ports, gives you half of the box for your downlinks and the other half for the uplinks. And now you can actually aggregate not only your bandwidth at such a spine, but you can also aggregate the links because you don't have to break them up going to the next layer. Now let's look a little bit further. So I'll give you here a little bit more of details. And these slides are very detailed, step by step by step. So have a look into it. And again, if you find a math issue, please send me a message. I want to see if my colleague did a mistake there when he checked my slides. But from a step 1, not building for the maximum leaf, when we go to a step 2, we repeat multiple fabrics, pots, however you want to call it. So when I look now that I have Fabric 1, Fabric 2, Fabric 3, Fabric 4, I can actually add much more fabrics. But now it's not anymore the fabric scale itself, these first two tiers which become relevant. It's actually more of how do I connect these tiers into my interconnect backbone on the top. So for you guys who look at ACI, we have leaf, we have spine, and what are we doing beyond the spine? It's called the IPN or the ISN, the IP network or interpod network or the intersite network. How do we call it in standalone VXLAN EVPN multi-site? We call it border gateways out there, right? So border gateways on the fabric layer and then above. So with this here, right, you see I already have the same amount of ports which I previously looked at either at the 8-slot chassis or at the 16 ports chassis, and I can connect that in various ways. So you see there my fabric blue, it's only connecting into fabric blue. So when you think of an ECMP way, the decision is made within the fabric over what plane you go. Is it blue? Is it yellow? Is it red? Is it green? So you don't have to go and figure it out at the tier 3, or sorry, at the top tier there, where it actually goes, because you will already know when you decided on the leaf going to spine 1 that you will stay in that plane blue until you reach your final destination. So it gives you a very deterministic path going through these planes. And now how big do I need to design these planes? Do I need to have big switches already up there and I cannot go from that big switch how I designed it in the beginning? I actually don't. I mean, this here gives you, I think it took a 16-port 400 gig in the tier 3 layer up there. So what am I doing when I'm ending up of these 16-port of 400 gig? What could I do? Well, there are a couple of options. As long as I have port left, I can bundle ports. And if I'm running out of ports, I can increase the box size, or I can actually add more boxes, right? Remember, our spine ports, or in this case, the tier 2, the fabric ports, we are going with half the ports down, half the ports up. So as long as I have ports on my fabric or spine layer, I don't know, this is not a pointer here. As long as I have ports left, I can connect to the upper layer. And it doesn't matter if I go fully meshed to all of these different planes or fully meshed to all of these guys up there. What I need to create is one deterministic port from my fabric, from a tier 2 to my tier 3. Because the redundancy in the fabric you have, and across or between the fabrics, the third tier up there provides as well, right? So if your tier 3 to tier 2 connection goes away, if your reachability end-to-end is impacted and you will not take that path anymore already on the decision on the leaf going to the first hop spine. Can I get a show of hands who saw that before? Okay. You guys haven't seen that before? 2, 3, 4, nobody? Okay, so this is what we do today. So we're not connecting every spine or fabric or tier 2 to the tier 3. Because if we want to do that, we need the same amount of ports at tier 2 as well as tier 3. And what does that mean? You have to go and write the new budget request to send some more boxes over. And I'm happy to do that for you and fulfill all these orders, obviously. But I also want to make sure that you guys are successful in your network designs, and it's not always about how many boxes you buy from Cisco. It's about how well your design goes and how scalable your design is. That's close to my heart. I can have different boxes up there. I think this is still a 16 I have there, but we have other variations of what we can do. We can do 32 port, 64 port, or 400 gig boxes up there, or we can just put some modular up there. We can do the same design with modular switches as well. Just remember, how many stages do we have when we add here modular systems? Anyone remembers? 3 stages in the modular? 11. Here we go. This is the count of stages you're actually creating in these different networks. So you have 5 stages in the 2-tier leaf spine. That's with modular on the top. You see there the 3-tier leaf spine with super spine, all modular. 11 stages. Is that bad? No, not particular, it's actually okay. But when it's 11 times 1 microsecond, is that great for you, for your application, for response, for round trips which are happening from ask to request? I don't know. Maybe it's okay. But it might prevent you from getting the full throughput. Now the bandwidth of your network, given the round trip times of small packets, increases the overall latency of your application response. And if the application response goes down, you will never get the big packets or the big transfers being sent over. Now, I want to give you a highlight on the very right. We said we can go beyond this 3-tier leaf spine, super spine kind of network, all modular, all interconnected. So we can build it in that evolved approach. Let's use fixed boxes, let's build these tiers on the top, and you see already that my latency goes down as a part of that. I have only 5 stages. I have it very deterministic given each switch is there. I actually might have some power optimization. I might have some cooling and space optimization as a result of it, because I don't have to reserve one single rack for all these different dots. I can put them wherever you want them. It's 2 rack unit or 1 rack unit. Doesn't really care, right? And then on the other side, when you think of power distribution, have you guys ever looked at what a 16-slot chassis requires in power? Is this like your standard build-out, which every rack has, that amount of power? I struggled a lot to put my modular switches in the racks in our labs because they're not built out for that. They're mostly built out for compute servers. So you have to get through all of these different thoughts and make the right design decision, what works for you, not just what works for you from a latency or application attribute, but also what works for you from a space, cooling, cabling, etc. And that gives you a lot of flexibility. So all of these are valid networks, all of these are valid designs, all of these give you scale. And when you look to the very right, I'll just give you a little bit of an example on how far you can go. I gave them 128. We scaled our VXLAN EVPN multi-site scale from 25 to 128 sites, 128 fabrics if you want so, multiplied by 128 leaves, multiplied by 48 ports, and that's the number you see on the very bottom there. What is it? Was it 700,000 or something like that ports in a single data center under a single management domain, meaning a single controller if you want so, a controller set, and manage that. I think we can go really big in these kind of networks if we want, but we don't. We don't have to, because we can start at the very beginning at a much smaller pace, that single fabric entity of 12 switches, 20 switches, 128, you choose. Now, I went through a lot of material with you guys. We only have 45 minutes together. I know it's much, but there's a lot of details in the slides which I put in. But I want to emphasize a couple of points which we rushed through in this session, which will bring you back to some earlier slides you saw. And I'm always forth and back to do a lot of technical content, or I try to give you to guide to more information where you can go. And I'd rather do the second one for these rather shorter sessions here. So when we look at what the conclusion overall is we can build small, or from very small, to very, very, very big. And we don't really have to build everything we knew from today. We can go a next step and evolve our design. So don't be shy. I don't lock you in. That's my main aim for this session. I want to make sure that when you come from a 2-tier network, you can go to a 3, 4, 5, whatever the scale is you need. But I don't want to lock you in, that you cannot walk forward with what you invest today or 5 years ago or in 5 years. The other key takeaway is bigger is not always better. You saw how small my individual entities were. You see these individual entities all built with fixed form factor switches. It doesn't mean it's worse. These days we have all redundant power supplies. And you remember from the beginning of the paradigm of the leaf spine networks, we don't have these single big failure boxes where everything goes away. So the outage of a single little switch might not actually hit you at all, because it's a fraction of what goes over that. And when you need to replace it, you can do that by just going to rack, pull it out. You don't need a whole team of people with the big arms to get that going. So it's a modern practice to do these things in that evolved way, and I think there are a lot of companies in the industry doing this for quite some time. More switches doesn't mean higher cost. Very often I hear, oh, it's so expensive because the modular gives me one switch and I use a fixed one, or I need 10 times the amount of fixed ones. It's so much expensive. It's actually not, right? The operational cost is a piece you want to consider in all of these cases. The power cost, the throughput cost per gigabytes or gigabits per second. These are the things you want to think about it. And these days we don't pay anymore by the pound or kilogram. We actually pay for the throughput of the boxes. As you maybe saw in some other discussions, when we were able to do 64 times 100 gig on 2 rack units, like 3 years ago, 4 years ago, now we quadrupled the bandwidth of 2 rack units into 64 times 400 gigs. So we came from 6.4 terabits, 4.terabit chips to 25.6 terabit chips. And it looks like we're continuing in that trajectory as we go forward. Now, I have a couple of more slides here. I would appreciate if you give some survey feedback if you can, if you feel. Appreciate it. Tell me what I do wrong. Tell me what I do right. Everything, obviously. I mean, nobody's perfect except me. Joking, sorry. And then as you want to go further through the week, have a look at what we provide when it comes to learn, what we train, and when it comes to certification. And remember, I had that other slide in the very beginning, which was talking about other sessions related to that. They will help you to even go more into that topic as we progress in this week. We have continued education, and with this, I'm going to let you guys go. I want to say thank you very much. I give you 2 minutes back, and if you have any questions, I will stay here for a little bit, and then hopefully see you soon again in one of these rooms. Thanks a lot.